Good morning, everyone. Okay, so here we are again. Okay, almost at the end of the semester. Okay, well, today we are moving on to a topic called AC steady state power. Okay, well, the world, the civilizations that we have had in progress, okay, has been sort of enhanced, by the society's ability to control and distribute energy. Okay, one of the way to so-called distribute energy, is by, converting it to electricity, and the electricity serve as the carrier for energy to us, the user. Okay, well, energy, we know that energy such as from fossil fuel or nuclear energy or sunlight, right, is converted into electrical power, so that we can transport it, and distribute it via transmission lines. Okay, so therefore the necessity to learn and understand the power, how to transmit it, to a long distance is very important also. So as we know that the world is pretty much, live on AC. Of course, there's some DC also. Okay, and so we distribute and the AC power for use. So today, this class, it would be the introduction topics that tells you what kind of power there is in AC world. Okay, so we're gonna start, okay, with the original power formula that we know, right, which is P equal to V times I. So as we know, right, if we have the current flows and there's a voltage drop, okay, across an element, right, and we want to find the power, okay, for this element. Okay, well, power to the load, okay, power to a load, okay, is simply, of course, the product of the voltage drop and the current that go through it. Okay, but this power in this case in AC we call the instantaneous power. So instantaneous power, so a small p here, okay, is equal to, right, P of t equal to V of t function V multiplied by function I, the current, right? So this is instantaneous power. So at particular time of t, right, because your AC would be in term of sine or cos sine term, right? So at particular time t, you get one value of V and I. Okay, so you get different values within one period anyway, right? Because you have a period, right? And then it will sort of repeat itself. Okay. For this, if let's say that the product of your voltage and currents turn out to be a positive value, it means that, okay, the power transfer, okay, is from the source, is transferred from the source to the load. Okay, if it's negative value, it means that the power is transferred, right, or flow from, okay, from the load back to the source. Okay, and this is also conventional sign, right? The current enters the positive and negative of the load, considering that this box is a load. Okay, well, of course we this is instantaneous power at particular time t, the values. We can't always like work on that. In our day life, you can't just go, okay, at this t equal to 1 second, the power is this much watt. If at t equal to 5 seconds, this is the power so much watt, right? So therefore, we come up with another term, and we also know that the power would repeat itself within the so-called the period, right? So therefore, we can take the average power for periodic instantaneous power. This is another formula. So there's the average power. So the average power P, okay, for a periodic instantaneous power P is, right? So therefore P is equal to, okay, 1 over the period T integrated from T1 to T1 plus T, so it's 1 period of the instantaneous power. This is the formula to find the average power, and the unit is watt. Okay, instantaneous power, the unit is also watt. Okay, so T is a period. Back to this formula. All right. Now, if we have, let's say that in case of we have V of t equal to Vm cos of omega t plus phi v volt, and we have a current equal to Im cos omega t plus phi I amps. Okay, so let t1 equal to 0 second. T is equal to 2 pi over omega. Okay, so therefore we're going to find the average power. Okay, so put it back in the formula. So we would have the average power is equal to, right, Vm Im over 2 pi over omega, right? I'll take the Vm and Im out. It's a constant. Integrate from 0 to 2 pi over omega. Okay, and you get cos omega t plus phi v times cos omega t plus phi I dt. Okay, now, right, you have to integrate this, but well, you can do it during your free time. Okay, you may use the relationship cos alpha cos beta equal to a half cos alpha plus beta, right, plus a half cos of alpha minus beta. Okay, so you would get average power P equal to omega Vm Im over 2 pi, integrate from 0 to 2 pi over omega. Okay, a half cos, right, 2 omega t plus phi v plus phi I plus a half cos of phi v minus phi I dt. Okay, you be my guest. You can have fun with it, right, during your free time if you like math. But we as electrical engineering, we're just going to take the formula, the final formula, which is P equal to, the average power P equal to Vm Im over 2 cos of phi v minus phi I. So this is the formula for the average power, and unit is watt. Is the unit, right? So that's the average power. Let's have a look at the average power for the elements, the 3 elements: resistor, inductor, and capacitor. So let's look at the average power for the first one, resistor R. Okay, so you have current I, let's say phasor I, right? R, and let's say phasor V, let's say, okay. And if we say that phasor V is equal to Vm angle theta V, phasor I equal to Im theta I, right? So the average power, the formula would be Vm Im over 2 cos theta V minus theta I. However, you should know that, right? The phase angle of the voltage and current across R for resistor, they are in phase. So theta V is equal to theta I. So if that is the case, you have PR equal to Vm Im over 2 cosine of 0, right? Because they are equal, which is equal to 1. So therefore, PR, the average power for a resistor, is Vm Im over 2 watt. Second element, an inductor, L, inductor L. Okay, L. Okay, so you have current going through it, induce a voltage across an inductor. Again, let's V equal to, the phasor V equal to Vm angle theta V, right? Well, if V is equal to Vm and the phase angle is theta V, right? Your current, the current for inductor, it's I lag V or I leads V. So please go back to the word civil, right? You're dealing with inductor, so you look at the last 3 letters, right? And you see that I comes after V, so that means it's I lags V by 90 degrees for an inductor. So therefore, the phase angle for theta I would be, well, it's lag behind, so it must be less than V, so it will be theta V minus 90 degrees for the current, for the phase angle of the current. So therefore, when you substitute it into your average power formula, it will become Vm times Im over 2 cos of theta V minus theta I, which is theta V minus 90 degrees. Okay. And you would get cos minus 90, right? This cancel out. Cos minus 90 is 0. So therefore, average power for an inductor is equal to 0 watt. Right. So that's an inductor. The third one is a capacitor, C. Right, again, current I and a voltage drop across the capacitor. So again, V is equal to Vm angle theta V volt. Okay, phasor I is equal to, right, phasor I is equal to Im. Well, go back to the word civil, right? For a capacitor, we take the first 3 letters, right? And I comes before V. So that means I leads V, right? So therefore, the angle for the current would be more, by 90 degrees. So plus 90 degrees amps. So therefore, substitute in the formula, P for the average power for capacitor is Vm Im over 2 cos of theta V minus theta V plus 90 degrees. So this cancel, you're left with cos 90, which is equal to 0. So therefore, again, similar to an inductor, average power for a capacitor is equal to 0 watt. So look at the three elements, we can conclude that a resistor load or a resistive load, R, okay, it will always absorb power at all time, while a reactive load, either C or L, okay, absorbs 0 average power. Okay, so that's the conclusion. Okay, so only R absorb average power at all time. So let's look at some exercise to prove that, to see if that's true with the values in the circuit. So so this is 25 ohms and this is L 120 millihenry, and this is Vs, okay, and this is of course the current I going through it, result in VR and VL. And the problems given that at steady state I of t equal to 721 cos 100t minus 41 degrees milliamps, Vs of t equal to 20 cos 100t minus 15 degrees volt, VR of t equal to 18 cos 100t minus 41 degrees volt, and VL of t equal to 8.66 cos 100t plus 49 degrees volt. So these are given values of functions for the voltages, okay, in the circuit, in the current. We want to find the average power delivered to each device. So I'm going to let's start with a resistor, okay, a resistor. So PR, okay, average power for resistor. So the formula is Vm Im over 2 cos theta V minus theta I. Okay, well, Vm is a voltage drop across R, which is 18. Current that go through R is I, so multiply by 721 times 10 to the minus 3 divided by 2. Cos of theta V of R is minus 41 minus theta I is also minus 41. So can you see that? Okay, they are in phase. The current and the voltage drop across R and the current through R both are minus 41, so they're in phase. So the answer is equal to 6.5 watt. 6.5 watt. Okay, now let's look at the inductor. Okay, same formula, Vm Im over 2 cos of theta V minus theta I. Okay, for an inductor, V drop across inductor is 8.66. Multiply the same current that passed through it, 721 milliamp, okay, divided by 2. Cos of theta V is 49 minus theta I is minus 41, right? And so the answer is equal to 0 watt PL. The last elements are the source. Okay, so Vm Im over 2 cos theta V minus theta I. So by now you may start to get a hold to the whole formula for the average power, right? Hopefully. Okay. So for the source, Vs is equal to 20 current, still same current flowing through it, what, 721 milliamps divided by 2. Cosine theta v, Vs is minus 15. Minus theta I is minus 31, well, 41, sorry. Okay. And the answer you will get is average power for the source by this formula is equal to 6.5 watt. However, if you look at the question asks average power delivered to the device. Delivered to device means that what you should have is that the current goes into the positive side of the terminal of the voltage drop. But if you look at the current direction for the source, the current enters the negative. Leaving it on the positive is not the same thing as the current entering the positive side of the voltage drop VR or VL. See that? This one goes in the negative side. So actually when your answer is positive for the source, when you do it like this, actually this means that the source is supplying 6.5 watt. Okay, so source supply 6.5 watt. So if you want to answer what is the power delivered to the voltage source, then it should be minus 6.5. So therefore power delivered to the voltage source is equal to minus 6.5 watt. Anyway, from the answer you see that the supply 6.5 watt. All that is absorbed in the resistor of the circuit. Okay, and the inductor does not absorb the average power. Okay, so next concept. So this is average power. So please remember the formula for average power. Okay. Next concept is RMS values. RMS stand for root mean square. So if you have so-called, you want to find, you have a current, right, and you want to find IRMS, it will be equal to, you take square, right, square, take the mean and then take the root. So you square your current, okay, then you take the mean, so integrate with respect to time at a period t, right, and then you square root it. Ta-da, like this. So if you do it for VRMS, it would also be square root of 1 over t, integrate from 0 to a period t of v square dt. So this is VRMS. Okay. So therefore, okay, if we have I of t equal to Im cos omega t plus phi amps. Okay, we want to find IRMS. Then it will be equal to, right, square root of, right, if of course t is equal to 2 pi over omega. Okay, so 1 over t would be omega over 2 pi, right, integrate of from 0 to 2 pi over omega of Im square cosine square omega t plus phi dt. Of course you can be my guest and do the integrations, but the answer for us to use is equal to IRMS is simply you take the magnitude of your current waveform divided by root 2. This is IRMS. So VRMS is also equal to Vm over root 2. Okay. Now, if we go back to our average power formula, P equal to Vm Im over 2 cos theta V minus theta I. I want to change this Vm and Va and Im into RMS values. So what do we get? Okay. So we substitute what Vm and Im is in terms of IRMS. So from the formula above, you would see that Vm is simply root 2 VRMS, right? Im would be root 2 IRMS cosine theta V minus theta I divided by 2. Root 2 times root 2 is 2, so it cancels out. So therefore, the average power is VRMS IRMS cos theta V minus theta I. Right? Or another formula is using the maximum value from the function would be Vm Im over 2 cos theta V minus theta I. And of course the unit is watt. Right? So in Thailand, right, VRMS is equal to 220 volt and our frequency is 50 hertz. Okay. And the voltage VRMS can be measured, it's a value that when you measure using the voltmeter. Okay, the voltmeter. Okay, so right, that's it, right, for the average power. So hopefully by next sessions that you're going to watch, you can remember this formula. Okay, average power is Vm Im over 2 cos theta V minus theta I, or if you use the RMS values, you simply have VRMS times IRMS cos theta V minus theta I. Okay, so that's it for the average power.